Okay, here we go. This is our basic outline for today. And we're going to do some clicking in just a second here, so get your clicker out, have it ready. You don't want to miss your clicking questions. And by the way, when we do clicking questions, it's wise to jot them down. Don't just like veg out, answer it, and then just keep going with your notes. They should be part of your notes, so jot down the questions as we go through. Now, we're going to talk about comets, and then we're going to talk in detail about Comet Wild 2 and what we have found about that comet. Now, the reason that we are especially interested in comets is because we think that most comet material is leftovers from the beginning of our solar system. And we really haven't talked too much about, migraine. What a day for a migraine. We haven't really talked about much about how the solar system forms, so let's take a look at it. Here's our basic pull quote from chapter 13:4. The comets are probably the most primitive objects we could study, preserved unchanged for billions of years in the deep freeze of the outer solar system. They're mostly icy objects with a little bit of rock mixed in there. Some scientists call them a dirty ice ball. Some call them an icy dirt ball. So there's a little bit of, planetary scientists have a little bit of, a few questions about that. But let me do a clicker question for you. Did you do your reading? Here's question number 1. You're on frequency DD. Read carefully. Arrange the asteroid and comet groups listed, starting with closest, then medium, and then farthest. There's an example there: Orlando, Fort Lauderdale, and Miami. Same kind of ordering. And let me look at your responses. Oh, brother. Okay, 15 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, we have a broad range of answers, and we have a scattering A, B, C, D, and E. No majority, and what that tells me is you guys did your reading. This should be basic. Did you hear what I just said? Basic. This is a kind of basic question that I might put on the test. I might even put this verbatim on the test. But if you haven't studied, you're going to be SOL. And that's what I say. If you study a normal amount, you're going to do okay on exams. You might not ace it, but you're not going to be in the tank. And right now, you guys are showing me that you didn't read. All right. Here's the correct answer. This is it, asteroid. Now, more people voted for this than anything else, but only 45% of the class. Now, I want to point something out to you on this. There was a majority of people that answered C and D. 27% of you, second biggest group, answered C. And I want to point out to you, for test-taking strategy, if all you can remember is that asteroid belt is closest, then that means you can reject A, B, and E. And then you have to do a coin flip, basically, 50-50 guess. Now, if you can get things down to that level, that's a little bit better of a guess than 1 in 5, 20%. Okay? So remember that. And hopefully you've heard instructors and teachers and stuff say this at the wazoo since 4th grade or whatever. But yeah, try to remember that. And make sure you do your reading, because if you don't do your reading, you're going to be... Did you figure out that there was a lot of reading quotes on the midterm exam X? If you didn't figure that out, I'm telling you right now, I put a lot of stuff in there verbatim from the readings. As a matter of fact, stuff that I had in lecture from the readings, my pull quotes. So now, when we say that comets are the leftovers from the beginning of the solar system, this is kind of what we mean. These are a couple stars that scientists have looked at. The left-hand object for HD 141943, that's what they see in infrared. Now, this is a false color infrared image. And then the right-hand picture there is kind of the model that they developed. In other words, if we could see everything about that star, that's what we'd see on the right. Now, same thing for HD 191089. On the left image is what we see in infrared. And then on the right over here, let me get my big cursor over here. This one, it looks you're kind of looking at it, but it's on a slant. And so is the other one. This one's really on a slant. All right, and you got to deal with that sometimes. You know, galaxies. And this is kind of like a swirly galaxy, except it's not a galaxy, it's one star system. Now, here's a really famous one. This is called HL Tauri. Go ahead and make a note of that. This is actually a diagram from your book. And what you can see in this one, and this is false color infrared as well. This is also from your textbook. Those dark lines around this star system, you know what that is, we think? We think that's big planets like Jupiter's and Saturn's, maybe even Earth's sized, that are sweeping. This is what we call sweeping. It's sweeping the nebula. It's clearing debris. Now, this is early on, all right? And the theory is that long, long ago, billions of years ago, our solar system looked like this one. And Jupiter and Saturn were sweeping up a lot, and the inner planets were doing their share, and Uranus and Neptune were doing their share. And so that's what we think we're looking at here. But they don't get everything. Now, this would be troublous trying to navigate through this solar system. All right? Because it still has a lot of debris there that's unconsolidated. But our asteroid belt is like this, and the Kuiper belt and the Oort cloud are like this as well. They still are not consolidated. In this star system, HL Tauri, most of that stuff is going to go into planets, we think, eventually. It takes time. But yeah, the process of sweeping is what you see here. So make a note of that, HL Tauri. We can see planets sweeping the protostellar disk. It's a disk-shaped mess of smithereens of stars that blew up and detonated into, zillions of fragments and smithereens, well before this one formed. And all those smithereens of stars, they swirled around in these big clouds, but eventually clumped up, and then it started spinning like this. And then the planet started sweeping out the outer part of the nebula. Also, the other thing here is the central object here, HL Tauri, it's also eating up stuff. I mean, our sun swallows comets all the time. If they get in too close, and we've seen it happen. In the past few years, we've seen a comet that we were watching, and as it went around the other side of the sun, it never came out. That means it got greased by the SUN. And we've seen comets blaze into Jupiter, Shoemaker-Levy, back in what it was, 1996, I think. And we knew that, everybody was watching it. And it blew a big hole in the atmosphere of Jupiter, ginormous, huge flash of light. And you can read about that one in the textbook as well on comets, or perhaps you have read it. All right, so let's look at the basic specs now. We know why we're studying comets, because they're the ancient leftovers. And, asteroids and meteorites, sometimes those are fragments of planets. So they're not quite as old. Some of them are, we think. Most of them are, but there's also some younger stuff, busted up planets and whatnot, and moons and stuff. So the Kuiper belt, we think, is this, it's kind of like an asteroid belt, but it's not asteroids, it's comets, and it's way out there past Neptune. Now here's a diagram. This is my diagram. It's like an overhead view, ultra simplified, and this black line in the middle, in the interior here, that's supposed to represent the orbit of Neptune. Now Neptune has an elliptical orbit, so this one's just a plain old circle, so it's kind of idealized. And then this greenish yellowish dot down here, it's big, it's supposed to symbolize the sun at the middle of everything. And then out past Neptune and out for about 55 AUs, 55 astronomical units, that's where we think the Kuiper belt is. Here's another picture of it. This was kind of a little perspective view. It's pretty nice. And you can see down here, down here in the middle is the SUN, and Pluto is this kind of yellowish line, and it's kind of slanted. And Pluto is considered to be a Kuiper belt object, all right? A dwarf planet. And let's see, this one here, this white line, let's see, Jupiter, Saturn, Uranus, Neptune. So this outer white line would be Neptune, and then Pluto. Now here's another picture of the Kuiper belt, or diagram, artist's conception, as they say. So it's kind of asteroid belt-like, but it's comets. It's not. And we know for a fact that the Kuiper belt is there. Why is it? Because we have seen it. Now the guy that proposed the Kuiper belt was a guy named Gerard Kuiper back in 1950. And he kind of worked out, okay, it's got to be about 50. He was looking at comets, and he was thinking, well, there's a lot of comets that are relatively short period, and they come through. You can close that up. There's a lot of comets that come through, definite periods. So he kind of worked out, mentally in his mind, there should be a reservoir, belt-shaped, like an asteroid belt, but way out past Neptune. By God, they found it. 1992, they think they measured the first one. It's called 1992 QB1. And then in 2002, an object that we now call Quaoar, I think that's how you say it. And actually, 2002 is when they officially discovered it, but they went back and they looked, and they found that they actually photographed it in 1980, and they didn't realize it. So that was actually the first time anybody laid eyes on it, but they didn't realize it until later. And we keep finding stuff out there in the Kuiper belt. It is not easy. You need big telescopes to look out there, and you got to have good infrared equipment, because a lot of this stuff it doesn't reflect a lot of light because it's so far out. Sedna, 2003. 2005 Eris, which is actually larger than Pluto. 2008 Makemake and Haumea, and those are like one is from Hawaii and one is, I don't know, Tahiti or something, Haumea. So they name them after these different, ancient gods of, well, it used to be the ancient gods of Rome, but they ran out of those, so now they're using ancient gods of Hawaii and stuff. Okay, so the Kuiper Belt's out there. We're seeing stuff out there. And we think that a lot of the comets that we see in the interior, when they blaze through the evening sky here on Earth, spend most of their time out in the Kuiper Belt. So the older comets we think are actually out here. And that's like a part of the solar disk, or I should say the pre-solar disk, the protosolar disk, that did not get cleared by Jupiter, Saturn, Uranus, Neptune, or anybody else. It's still out there. So that disk we saw for HL Tauri still had a lot of stuff showing up. You could see it was getting cleared, but wasn't finished clearing. This one's out there. It's never going to be cleared. Except possibly, actually it's slowly being cleared, but it's going to be billions of years before that gets cleared. Because Jupiter and the Sun do eventually budge these things out of their orbit, and they have collisions and stuff sometimes. So if they have a collision, that'll bump something into an orbit that slides down into the inner solar system. Now, the other really big object, or the other big grouping of comets, is called the Oort cloud. And so this is number 2. It's really, really ginormous. And this was developed, the theory of this was developed by Jan Oort, another guy from Holland, to explain long period comets. And we haven't seen anything out in the Oort cloud because my wonderful students, the Oort cloud, the theory of the Oort cloud is it is way out there. So it's going to be really hard to see. It's not stuff that produces its own light, and it doesn't reflect much starlight because it's starlight. Did you hear what I said? Starlight. They're far enough out there. They're a good fraction of the way to the Alpha Centauri, the nearest star, out there in the Oort cloud. They're out there, so they're not going to reflect a lot of sunlight back towards Earth. But people are looking, and we know that Hyakutake, Comet Hyakutake, which came through in about 1995, 96 in there somewhere, which I remember seeing that when I was in grad school. And all the guys in the physics department were taking photos and stuff. Comet Ison, ISON, and others, they have really long periods. So Hyakutake, it's like the period for Hyakutake is like, I don't know, either it's tens of thousands of years. I want to say 40,000, but it might actually be 70,000 years. And the reason, how do they know that? Well, because what they do is they track it. When it gets to the inner solar system, they figure out the shape of the ellipse, and they figure out where its perihelion is, what its velocities are. They work out all the Sir Isaac Newton calculus and velocity and stuff and trig, and they figure out, the semi-major axis for Hyakutake means that its period is going to be, tens of thousands of years. So I think it's definitely not going to be coming back to see us, but something else might be on its way right now. So you keep alert. Now here's a picture of the Oort cloud, and this one is a NASA image actually, and up here at the top, you see a little inset? This one? Yeah, that's the Kuiper Belt, okay? So, and which we've already taken a look at. And you can see Pluto's orbit is the yellow. It doesn't really look yellow on this screen, but this one here where my cursor is, there's kind of an orangey reddish one, and that's a typical Kuiper Belt object, supposedly. And then inside of that is Pluto, and then the other planets. But the Kuiper Belt, compared to the Oort cloud, is really shrimpy because it's see this little blue thing down here? That's the Kuiper Belt. We can barely see stuff in the Kuiper Belt, right? We're just a little blip down there in the middle of that blue blob down there. The second biggest part of the solar system, the Kuiper Belt, is a little blob, and we're a little speck down in the middle of that. You couldn't even see it with a microscope. And so the Oort cloud is way out past that. So it's ginormous. And here's a pull quote from chapter 13:4. Oort suggested that the new comets we were seeing, like Hyakutake and Ison, were examples of objects orbiting the sun near the edge of its sphere of influence, and whose orbits had actually been disturbed by nearby stars. And so Hyakutake, we don't know what budged it out of its orbit. It might have been Alpha Centauri C. Right now, that's the closest star to us from the Alpha Centauri triple star system. Alpha Centauri A, B, and C. And right now, C is the closest. And so Alpha Centauri C, it's a little red star. Not very bright. We could see it. We found it. And that might have been the thing that shook Ison or Hyakutake out. And we know that other stars over the eons, billions of years, have, swung by our planet, or our solar system and stuff, and perturb stuff out of the Oort cloud. So now this makes it look like the Oort cloud is like, you got to really dodge your way through it. And that's probably not true, just like the asteroid belt. To make it appear on the screen, we have to put 1 pixel size dots there, white colored dots, but you're not, it's not like a shooting gallery in there. But we think there's trillions of comets out there in the Oort cloud. And that the Oort cloud extends most of the way to, or a good fraction of the way to Alpha Centauri. So, matter of fact, some people think that stuff in the Oort cloud was captured from other stars as they passed by us. So that'd be kind of cool. But it's going to be hard to get out there and, getting a sample return. If we don't have like warp drive, like in Star Trek, some people think that actually can be done. Some of my classmates in grad school were actually trying to work on that, and time travel and warp drive and stuff. And but I mean, some people figure we can do that, but we just don't know how to. We haven't figured it out yet. But that's what it would take to get out there, because it's way out there. I mean, we got stuff going through the Kuiper Belt. We're heading for the Kuiper Belt now, but the Oort cloud is like a dream. But eventually somebody will get to observe it, or figure out some backdoor strategy to find something, maybe something big in the Oort cloud. There might be big stuff out there. All right, let's talk about isotope ratios. We're still in the same session here. Where is it? No. We don't need the grade book. No.
Oh, you want it quicker?
Yeah, we should be in a session. It's open. Yeah, just click on this. Yeah, click out of that. All right, so we're going to have 2 sessions today. All right, don't close it. All right, keep that open. All right, isotope ratios. Now we're going to get down to the nitty-gritty of something really cool that we've seen in the Stardust spacecraft that went out to visit Wild 2, one of the comets that's easy for us to get to. And to do that, we're going to have to talk about isotope ratios for oxygen. Now, oxygen isotope ratios and hydrogen isotopes and stuff are usually done relative to standard mean ocean water, SMOW. So first thing you do when you're trying to figure out the ratio, what we call the delta 18 and the delta 17 ratio, first you got to write down the abundance of oxygen 18 and the abundance of oxygen 17 in the oceans of Earth. That's our reference. You know, and when they're doing carbon isotopes, they actually use a limestone formation up in South Carolina, the carbon in that limestone, calcium carbonate. But for us, we use ocean water for oxygen. Now, let's say that you have a meteorite. It's fallen to Earth, okay? And you've analyzed it. You've put it through one of these ginormous, the ions going through a magnetic field, and the big ones curve in bigger circles into their collection cup, and then the smaller ones curve in a tighter circle into a different collection cup, and then you count them up. And let's say that your analysis for oxygen 18 is a little bit higher, 2406 parts per million. All right? Now, ocean water, standard mean ocean water, for oxygen 18 is 2005.20. But what your meteorite's got is a little bit richer than that. All right? And we're going to calculate the delta 18 ratio. Now, this is the formula that you're going to want to calculate. Jot this down. We're going to walk through it. It's not too bodacious. You basically take what your lab tells you about your meteorite, and that's in the numerator up here. Okay? So for us, that's going to be 2406 ppm. And then down here in the denominator, you put, for oxygen 18, you put 2005.20. You know, you look that up in your handbook of standard mean ocean water. All right? Okay, then you take that ratio, work it out to whatever it is, and we'll do that together here in just a second. And then you subtract 1. And that's what we call the delta 18. And basically, go ahead and make a note to yourself. The delta 18 oxygen ratio tells you how much your asteroid deviates. D for deviation. Delta. D for delta. D for deviation. Difference. How different your asteroid is from the baseline, ocean water. All right? Question?
You're going to receive both of these numbers, right? So when doing a problem, your number and...
Yeah. It'll be this. You're going to have... Well, I'm not going to tell you what's on the exam. But if I were to put something like this on the exam, the SMOW would be on like the cover page. And then the problem would say, all right, your asteroid is, whatever. And that's what we're doing right now, so take good notes. And hey, you guys, you're going to be clicking in and answer here in a second. So take good notes, get your clicker out, and keep it out, and get your calculator out too. All right, now, for just to have another ratio, we're going to do delta 17 oxygen. And let's say that you're a little depleted, 342 instead of 379.9. All right? There's, it could happen. All right? So that's our example. And what we're going to do is get the delta 18 ratio. We're going to do that one together. And then you guys are going to do the delta 17 ratio on iClicker. Okay? So let's get down to business. All right, now the first move is to put in your numerator and your denominator. So this number up here on top, that's what the lab guys tell you. So Tricia, when she's in the lab, she'll come back to you saying, all right, 2406 ppm. And then you go and look up your handbook of standard mean ocean water, printed by Professor von Schmidt in Vienna, or wherever it is. And it says 2005.20. So that's your baseline. So we're making a comparison with that. And what this does, the minus sign in there tells you how different is your asteroid from standard mean ocean water? All right. Now, go ahead and calculate that quotient. Use your calculator. Your phone calculator is okay. But on exam day next Tuesday, bring your real calculator. You're going to need it. Cell phone calculators will not be allowed. All right? They're both pretty close. The numerator is a little bit bigger than the denominator, so it's going to be 1 point something. Who's got a number? Blue shirt man, what do you got? Is that young lady? Is that what you've got? 1 point. What do you have? .1998. Oh, so you already subtracted. Yes. Okay. Yeah. So subtract. So okay. So there's your number, 1.19988, and then subtract 1. Ching. All right. Now, so there's your answer. There's your delta 18 oxygen ratio. All right. It's a number. All right. It's not measured in meters, seconds, or anything. It's just it's a percentage. Matter of fact, if you round that off to 2 significant figures, what percentage would that be? 20%. All right. So go ahead and write down 20%. Now, the traditional unit in these isotope ratios is not percent, it's per mil. Okay, per mil. Now, per mil is basically parts per thousand. So if you have 20 parts per 100, you have 200 parts per thousand. Now, look at that symbol. It looks like, see that one at the very bottom? It looks like a percentage, but it's got 2 zeros down there. That's the per mil symbol. And if you have a Mac, it's in your, emoji and text panel that you select. That's what I did. So it's in there. That's the per mil symbol. All right, now, this means that your delta, and we know that your delta 18 is a little bit more enriched. Anytime you have a positive delta, you have an enriched asteroid, or whatever it is you're testing. Okay? And so this one is, a 200 is highly enriched, especially for an asteroid. But that's you let the numbers do the talking. And you just write down your result, 200, that's what you go with. So this one, now, when you're doing your clicker question, which is coming up, you're going to answer in per mil, okay? So make sure you kind of get your mind around that. Matter of fact, let me pause for questions about this calculation. Yes? If it's negative, well, delta 17 is going to come up negative automatically, and that means you're depleted. That means the difference is, it's like in accounting. If your checkbook is a positive balance, you're rich. If your checkbook has a negative balance, that means you're overdrawn. Okay? All right, so we're going to get a negative delta 17 out of this asteroid. And you use the same formula, okay? But the -1, see, if the numerator is smaller than the denominator, that quotient is going to be less than 1. And so something less than 1 minus 1 is going to be a negative number. So it'll come out naturally. Another question. Yes?
Why is it 200? Like, where did that come from?
That's the per mil rating. All those 3 last numbers are equivalent. All right? 0.19988 is perfectly fine. That's your delta 18 oxygen ratio. But a lot of times people want to know, a ratio, they want it in a percent. Okay? Like for GPAs and stuff. Okay? That'd be 20%. But in isotope ratios for geologists and astronomers and stuff, they usually go per mil. So that you just basically just you rub out the decimal point, and you take the next three numerals, and actually the next four, and maybe round up your third one, which we have done here. So instead of 199 you could say 199.88 per mil, but if you just want to have three significant figures, you'd write 200 per mil. Jordan?
On the next clicker question, are we also rounding?
Yeah, and I'll give you an example for the clicker question. But before I do, let me show you about good old ALH 84001. It is enriched, but not nearly as much as our example. Delta 18 oxygen is about 0.460, and we've got a bunch of other meteorites bagged and tagged, as they say. Matter of fact, here's a lovely graph from the University of Hawaii. This is the Planetary Research Discoveries website. And you can see they've mapped up Delta 18 on the horizontal axis and Delta 17 on the vertical axis, and then they plot them, and actually they find patterns. You know, that all the things, all the chunks of Mars are kind of up here in a group, and that the Vesta meteorites that we know are from Vesta, they're down here, and everything from Earth and the Moon is somewhere. They don't plot them out because there's so many. The oxygen isotope ratios are on that line. That's called the terrestrial fractionation line. So different sized chunks have different ratios, but they do seem to form these linear patterns on this kind of a chart. Here's another one. This is what we call a triple oxygen isotope graph. Go ahead and eyeball it. Right here in the middle, this blue dot where the two axes cross. Okay, here's Delta 17. 60 here, minus 60 down here, but in the middle, 0. That's where SMOW is. Okay, and that's what they've got here, SMOW right here. And see, oxygen 18 goes from 60 to minus 60. They don't have minus 60 labeled, but that's what it is out here. And so right in the middle is SMOW. And then Mars is over here, and here's some asteroids, and some meteorites called chondrules, calcium, aluminum inclusions, molecular cloud oxygen. You know, they got different things marked out on this one. And we're going to be making our own one here in a few minutes. All right. Hit the refresh key, my wonderful students. And now, Jordan, we're going to hack this Delta 17 ratio calculation. And I got everything in here. I think you can do it. All right, now it's going to be negatory. So you're going to, here it is. Go ahead. You can start the question. It's numeric. You're going to want to lead with a negative sign. Okay, hit your refresh key. All right, because we switched from multiple choice to numeric. All right. All right, so you enter, and I think you're going to have to enter a minus sign. You should be getting a negative something. And the reason for that is, as I mentioned before, it's slightly, we would say it's depleted. All right? Anytime you get a negative delta ratio, and definitely talk with your neighbor, coordinate and kind of kibitz. If you're a little, it's a little bit different. But this is the real thing that astronomers do, you know, when they're trying to sort out what kind of a comet, what kind of an asteroid, what kind of a meteorite have we got. And we want to know all about these bad boys. All right, now, who was asking me about rounding off? For those of you that are trying to figure out, per mil. Young lady up here with, you asked me about per mil. See, you take out the decimal point, and then the next 3 digits, and maybe the 4th one, okay? And you keep the minus sign in this case. So now the first digit is a 0, so you don't need that one. But you do need the 4, the 5, and then the next digit will tell you, should I go up to a 6 or keep it as a 4, 5? 4, 6, or 4, 5. So the 4th digit will tell you that, and so this was minus 45. Basically what you do is, yo, what is your name again? Natasha. Basically what you do is you multiply by 1,000. Yeah. And then, maybe round off to how many digits you want. So. All right, let's take this one and this one. Go see if we got anything else that might be acceptable. Yeah, you go ahead and accept that one, if you can. Well, wait till we finish it. Okay. How come you were late today? Car trouble? Ooh, okay. What class was it?
Aerospace design.
So a Bearcat.
Yeah.
Tough test. Yeah. So just one midterm for that?
We have 2 and then a final.
Lord. So is this your first or your second midterm?
First.
So he got blazed up just the same as we did. Did he have to change the...
Had to change some things around.
Yeah. That's Hurricanes for you. Well, I'm glad to see you here. All right, how many we got? 168. All right, I'll give you one more minute. Yes. Yeah, SMOW is 370. Yeah, for oxygen 17, it's 379.9. Yeah. You were supposed to write it down. Okay. Yeah. Jordan. Yeah, follow that pattern there. All right, just like I was explaining to Natasha, you take away basically multiply by 1,000, and then so if you take negative 0.0453 and multiply that by 1,000, that's going to be 45.3. And then I just want a whole number of per mil, parts per mil. Okay, so 45.3, type in 45, negative 45. Okay, so don't, all right? So you can, Jordan, there's a bunch of different ways, that you mentally do it, but that's one way. Hold on a second. In the back, yo. Yeah, if it was 455, you'd go up to negative 40 or down to negative 46. If it was, but it's 453, negative 0.0453, so you go down to negative 45. Is that the same question? All right. All right, how many doing there? Okay, 15 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Anybody come up with negative 100? Raise your hand if you got negative 100. Sweet. Okay, report to Robinson Observatory for research duty Thursday night next week. I'm just kidding. A lot of you guys got it. I see a bunch of you got negative 99. You rounded off a little bit. Somebody typed in negative 99, 4 people, negative 99.8. That's good, but it's not rounded off right. So, I see somebody with negative 98. Anything else? Negative 99.8. Yeah, so, okay, I see some couple errors and stuff. I'm going to be giving you a homework assignment this weekend. It's mainly practice calculating your delta 18s and your delta 17s. So, final note on this, you would say that this asteroid is depleted of oxygen 17. It's enriched of oxygen 18, and it's depleted of oxygen 17. Now, and so you may say to yourself, well, Dr. B, is that possible? Oh, yeah. There's all kind of chemical processes that prefer oxygen 18 over oxygen 17 over oxygen 16. For instance, rain in water. If you've got an oxygen 17, it's going to fall first. You know, so if you've got an H2O with an oxygen 17 in it, it's going to fall as rain or snow a little bit sooner than an H2O with an oxygen 16. All right? So these ratios, not only do they help us identify stuff, but they help us figure out the chemistry and even the nuclear reactions that are happening. And we'll get to that in a minute. Now, I want to give you some real data. All right, now we're getting down to the nitty-gritty. All right? I don't want you to write this down. You can write down a couple lines, I guess. I've got a bunch of objects. The name, and there's NWA 7304. We talked about that little hunk of Vesta. And a bunch of other ones. Yamato, that's a Martian meteorite. We got a bunch of Martian meteorites. Here's LH 84001. We talked about that one. Lynch 002, that's a lunar meteorite. Yeah, a little hunk of the moon got blasted off. You know, some asteroid smashes into the moon, makes a big crater. Some of the smithereens get ejected into space and land on Earth. And we can, you know, now that we've had Apollo astronauts bring back moon rocks, yeah, we know that those babies are from the moon. They fell as meteorites, but they're just like the moon rocks. All right, now, go ahead and make a note. I've got a list of objects, write down a couple. I've got the delta 18 ratio, and I've got the delta 17 ratio as well. And I've got a little blurb over here about what class it is. So I have 3 from Vesta. I have 3 C-type meteorites, CM2s. That's a meteorite class. I've got 3 Martians, 3 Martian meteorites, and 3 lunar. And then I've got McKeegan, the very last one. Better write down McKeegan, because McKeegan is what we are talking about today. As much as I love talking about Vesta, Mars, and the moon, McKeegan is the topic. McKeegan is the target. Now, don't bother jotting down all these things. If you want, you can jot them down later. Look at them in YouTube. But I'm going to show you how they plot up. Now, if you use the delta 18 on the horizontal axis, as some of those other diagrams I showed you, and the delta 17 on the vertical axis, here's how these real live data graph up. All right? That I think you can make a sketch of. All right? So this graph starts at 4 and it goes down to -3 on the delta 17 vertical axis. All right? And then it goes from -1 over to +9 on the horizontal delta 18 axis. Now, SMOW is 0 and 0. So right down here where my cursor is, I'll put the blue dot in there in a few minutes for SMOW. That's where it would be, right there. All right? Now you can see the red ones up here, that's the three Martian meteorites. Okay, so give them a little, and you know, they do fall on linear patterns. They're called fractionation lines. All right, so here's the Vesta, these blue triangles pointing downward, that's Vesta. V for Vesta, downward pointing triangle. And then Mars for the upward, the red ones, that's Mars. And then over here, the yellow diamonds with the black outline, that's the moon. And you can see that those are all pretty tight. They're all fairly close together. You know, the moon and Vesta, Mars. And I don't have any rocks from Earth here, but you could, you know, easily do some, you know, a hunk of granite from Vermont. You know, and a hunk of basalt from the Atlantic Ocean, and a hunk of basalt from the Columbia River Plateau, and a hunk of basalt from the Deccan Plateau in India, etc., and a piece of sandstone from Australia. You know, do all those, they'll be up there by these, you know, Vesta and Moon and Mars and stuff. Now, check this out. These are the C-type meteorites. Now, they're in a different group. And I've only got 3 of them plotted up there. But yeah, they do form a line. And let me, now I know you're sketching this, and I want you to finish sketching it. But now look at, here's the one from the Hawaii website. Look at that one. See that? Mars is the red ones. That's Mars. A little bit higher up and to the right of Vesta. All right? And this doesn't have the chondrules on there, the chondrites, but you can see the vestige of. So if we were to plot up some more Marses and some more Vestas and a bunch of Earths, here's the moon up here, it would start looking like that one that we were just looking at. So it would start to look like this, right? If we had more data, but we're just plotting up a few of them, all right? So down here is my Vesta. Now, here's SMOW. Here's my blue dot. Okay. That's the water in the oceans of Earth. Average. The mean. So it's, you know, somebody could have said, well, let's make my oxygen isotope baseline the ice that fell in Greenland 2,000 years ago. You know, we could have done that. Or the ice on top of Mount Everest in 1953. You know, we could have done that. But they decided that, you know, the ocean water is more convenient. It's everywhere. So that's what we use. All right? Now, let's get back to my data table. So hopefully you got a good sketch. And if you don't, you know, you've got a start of it. And you can go back and look at the YouTube. Now let's take a look at the data down at the bottom. What happens when we graph up McKeegan? Go ahead, make sure you have those ones down there. Delta 18 is negative 117. Delta 17 is positive 1660. Oh my goodness. Way different from the other numbers, the asteroids and stuff. But you may be thinking to yourself, Dr. B, what the heck is a McKeegan? Well, a McKeegan is a person. Kevin McKeegan, he is the man. He's a professor of planetary sciences out at UCLA, and he is the one that found the McKeegan particle at the bottom of that table. He and his, you know, all the people in him. Now, he's a specialist in isotope ratios. Here he is. It's pretty nice. You don't have to write this down. I'm going to give you the reference. You can go look it up through the UCF library website. This is from his article in Science a few years ago. Yeah, this is hydrogen. See that? This is D over H. Now, these are just the abundances. This is not the delta ratios. Okay, so but it's D over H relative to SMOW. And we know what that is. And he did that. He looked at the stuff from the Stardust spacecraft, and he analyzed it for hydrogen. Here's another one. This one's carbon and nitrogen. Now, this is what we would call a triple isotope chart for carbon, but now it's not oxygen and oxygen, it's carbon and nitrogen. All right, and scientists study that ratio as well, right? And this is a slide from his article. They provide PowerPoint slides. This is one of them. And Professor McKeegan and all his associates, they mapped this out. Kind of like what we just did. Except they did it from something that came back from space. Can you imagine how valuable that stuff is? Billions of dollars spent to send that spacecraft, and maybe they have a gram of material in all, for that whole journey, a gram of material, but they analyzed it. And carbon and, here's another figure. And this, my wonderful students, is figure 3 in McKeegan's article. Make a note of that. If you want to look at this in detail, it's figure 3 that you want to look at, and what he talks about with figure 3. And you may say to yourself, Dr. B, what is figure 3 in the McKeegan article? Well, it's a set of 4 images. You can see an isotope plot in the bottom right. We already know about that stuff. But let's take a look at this thing in the upper left. That, my wonderful students, is a bullet hole. From the Stardust spacecraft, the collectors were supposed to be the big or the little slabs of aerogel, silica aerogel. And they did. They captured a lot from those. All right? But it was in an aluminum framework, and some of the stuff just banged into the aluminum. And that's what this is. It's a bullet hole in the aluminum framework of the collector, that tennis racket object. And so they looked at that. They looked at the aerogel, all the stuff that was captured there. And then they looked at this, because this has a little piece of residue. See where it says residue there? There's a close-up of it. And that piece of residue, they put in their analyzer. See this little circle here? That, my wonderful students, is McKeegan. That is what we are looking at. Now, here's the oxygen 17 false color. This is the abundance chart. So they mapped out the oxygen 17 abundance relative to oxygen 16. They calculated the delta 17 for every part of that residue fragment. And this thing right here in figure 3, that is the hot spot. That is the thing at the bottom of our table. That is what we are studying. All right, so here's McKeegan. It's this thing right here. All right? That's delta. Look how hot it is. Look how enriched. It's way up in the red. What's our delta 17 ratio for McKeegan? What does your data say? Go on, look at your notes. 1660. It's way up in the red. So here's our chart. These are asteroids and stuff, or meteorites, I should say. These are all lovely, very nice. But when you try to put McKeegan in on this graph, it is way out of the pattern. There it is up here. Look at that. Let me move this out of the way. All the SMOW stuff All the asteroid or the meteorites, they're down here in this little blob down here. And up here, this is McKeegan. My wonderful students, McKeegan is definitely out of the asteroid pattern. McKeegan is definitely out of the meteorite pattern. This is it down here. Moon rocks, pieces of Mars, pieces of Vesta, C-types, Earth, it's all down here. This little blob down there. And here's McKeegan up here. Oh my goodness. Now here's the kicker. This is why we are studying McKeegan today. This isotopic composition, way enriched in oxygen-17, but yet depleted relatively of oxygen-18, is typical for pre-solar oxide and silicate grains belonging to group 1. Group 1 is a group of particles that he analyzed in a previous paper. And here's the kicker. It is thought to, this is McKeegan writing this, and his companions. This isotopic composition is thought to originate in red giant stars or asymptotic giant branch stars. So what they found is a piece of star millions of light years away and billions of years ago that detonated in a supernova explosion and eventually swirled down into comet Wild 2. Many millions, possibly even thousands of light years away, long way away. Why do red giants, and our star is not a red giant star. Betelgeuse is a red giant. Antares, they're red giants. Why do they produce highly enriched oxygen-17 and yet depleted in oxygen-18? That will be our topic after exam 3, when we study, as we're going to turn to the evolution of stars, including our sun and all the other stars that we know about. All right? Now, that completes my discussion for today of exam 3 material, but I want to talk about exam 3. And I want you to listen carefully. Did you ever see that movie, The Terminator 2? And Arnold, he cuts his arm off and he reveals that he's a robot. And he says to Miles Dyson, he says, "Now I want you to listen very carefully." And that's what I want you to do now. I want you to listen very carefully. Basic specs, same as before. Scantron, and you definitely need a calculator this time. There's a calculator. One of these jobs, something like this. This is TI-30X-IIS. Get it at the bookstore. Somebody just left it up here. Cannot use your cell phone. Pencil and eraser. Those of you that had blanks last time, make sure you do not forget. Most of you forgot. There's a few of you that didn't darken in your bubbles properly. And you'll know that by looking in web courses. Bring your eye clicker. Now, a student over here on the left side of the room, I don't know where he's sitting today, asked me a couple weeks ago before exam 10 or exam X, what's the most important thing on the test? And at the time, I was a little bit brusque because I don't usually give out study guides, and I'm not going to give you a study guide. But now I think back, Exam X, you know what I was thinking about on that test? Elliptical orbits, Kepler's third law. If you could figure out everything that I was talking about for Kepler's law, third law, you figured out everything else. All right? Or you have a good chance to have learned everything else you needed to learn. Now, on this one, exam 3, McKeegan. Oxygen isotope ratios. Everything that we've been doing for the past 2 weeks has been aiming for this. That being the case, I'm going to have some readings for you to do. I'll post a link to the McKeegan article. You can go, and it's highly technical, even for me. But you can look at the diagrams. We know what the diagrams mean. Most of them, anyways. There's a couple other really cool articles where they actually take the bigger grains of dust and they actually drill holes in them and analyze this. They extract what they drilled out and analyze. It's kind of cool. I'll make a homework assignment this weekend. Maybe 1 or 2 multiple choice questions, but definitely some calculation practice for delta 18, delta 17 ratios, just so you can, practice your burp off and make sure you know. Because even though I'm not going to tell you what's on the test, if you know how to calculate those things, you'll be pretty happy on Tuesday. Any other questions? All right, dismissed. Come on up if you have questions. And I'll see the rest of you on Thursday, or Tuesday. Hi. Where's my cursor? Come on, baby. There we go.